Okay, welcome back. Second part, reaction rates. And I left off talking about, well, how is it that we determine how fast a reaction goes? I mean, it really could be, if you can tell where the equilibrium point is, a matter of taking out a watch and just timing it. So this statement in your book says, well, we can take a look at a reaction and we can measure the reaction in terms of how fast products are appearing or how fast the reactants are disappearing. What they do is they choose whichever one's easiest. For instance, in our lab, we would have done a bleach reaction lab where we have food coloring and then you add some bleach and then the color disappears. Once the color's disappeared, you stop the watch and you record how fast it takes to consume by the bleach all of that food coloring. So again, whatever's easiest. If you're producing, your four signs of a chemical reaction: precipitate formed, gas evolved. Again, as heat exchange. As long as you can tell where the equilibrium point is, you can use any of those to determine how fast the reaction's going. And it doesn't matter whether or not you take a look at the forward or the reverse, because at equilibria, the forward and the reverse reaction are occurring at the same speed. What I do in my organic class is we'll run a reaction that takes hours, and we'll let it run for 10 minutes, and then we'll pull out a sample of it with a syringe, and we'll add what's called a quench, which is a chemical that stops the reaction, and then we'll titrate it, which means we'll react it against something that we know the concentration of, and we'll compare the concentration of what we're titrating and determine how much of it has reacted. All right, so what is concentration? How is it measured? Which units? What would be the unit for reaction rates? So quick review. This goes all the way back to what we did when we were talking about solution concentration in October. Okay, what is concentration? We said concentration was a ratio, and in concentration, let's just write C for concentration. We have the amount of solute divided by the total amount of solution. And a lot of times what we'll do is, remember, solution is solute plus solvent. That can be expressed a lot of different ways, including density. Density is a concentration unit. But most commonly it's in molarity. that is not an M. And remember that molarity is moles of solute divided by liters of solution. And when they use brackets and they put brackets around something, what they're saying is that this is the molar concentration. So this would be the molar concentration of X. Now, we've used brackets before. We used brackets when we were doing Lewis structures. For instance, if we had nitrate, we put brackets around that, and then we put the charge of the polyatomic group outside the brackets, and we used a double arrow to show resonance. There's another structure here, but I'm not going to waste time drawing it. So we've used double arrows before, but different set of double arrows. And these double arrows are for resonance, and the double arrows that go left and right like that are for equilibrium conditions. So they're not the same double arrows. Oh my goodness, it's taking me forever to finish this Lewis structure. And then there was a third resonance structure for nitrate, where the double bond was shifted between the nitrogen in the center and the oxygen on the east side. But the other use of brackets in chemistry is to say molar concentration of something. So the units for concentration is moles per liter. So what would the unit for reaction rates be? Reaction rate would be the change in concentration of X over some unit time. Usually it's in seconds, it doesn't have to be. So our units would either be molarity per second, for instance, or moles per liter seconds. Again, it doesn't have to be seconds, but seconds is the SI unit. Okay, what are the 5 factors that determine the speed of the reaction? So we have to take a look at all 5 different ones. All of this comes down to collision theory. The more collisions you have, generally the faster the reaction. Now, not only do you have to have more collisions, but the collisions have to be successful. Again, right time, right place, correct angle on the functional group with enough energy to break bonds. So you can increase the number of collisions, but if you don't have the proper orientation, then you still don't get a reaction. But in a general sense, if we look at the nature of the reactants, certain things react faster than other things as a general rule. For instance, ionic tends to react faster than covalent. Concentration of the reactants. The more reactants we have, the more collisions we have per second, the faster the reaction. Temperature. The more heat, the faster the particle movement, the more collisions per second. Not only that, but you also increase the energy. We'll come back to that. Amount of reactant surface area. If we grind something up into a powder, it will react faster than if we leave it in a clump. And the presence of a catalyst. There are chemicals that help with the orientation of the materials. Now I'm going to go through this video. I'm going to stop it at one point because there is one thing I disagree with on the video. And again, you may hear that slight echo in the background, so I am going to provide the link. So if you want to go and watch the video via the other link so you don't have the echo, you should, and then come back and watch it with me so I can go through and make that one correction.
One of the most challenging parts of meditation is what's sometimes called
Skip
the
ad.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel.
Okay, that's where I have to pause it. Look, just because you make the container smaller, that doesn't mean that you've changed the concentration of what's inside. If it was a gas, you would change the concentration by making the volume of the container smaller, because now the particles have less room to move around. But think of it this way. Let's say you had a drink that was real watery, like fruit punch watered down or something like that. Putting it in a smaller glass isn't going to make it taste sweeter. You got to get rid of some of that water. And that's what they're trying to show. They're trying to show a change in concentration, but the way they did it isn't really correct.
Or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay. So the five factors. First of all, nature reactants. They say things with bond rearrangements. In other words, things that have to change shape before they can react actually take longer than things that don't. Like, for instance, in an ionic reaction, as long as you dissolve it in a water environment, the ions are free to move around and they can react faster. I'll give you an example of bond rearrangement. Because we had kind of talked about this a little bit when we did structures. Most stable structure would be following an octet, which is the tetrahedral structure. So in a tetrahedral structure, you have a central atom, and then you have the 4 things connected to it in a tetrahedron that are surrounding it. Now remember that each of those 4 things surrounding the central atom, they have electrons around them, so this creates a negative charge. So when a particle approaches it, let's say we have a reaction particle here that we want to, let's call it particle A, that we want to react by hitting the central atom, it's repelled by all 4 of the atoms that surround the central atom. So there's no way to get in there and attack it unless you really raise the heat. I mean, if you raise the heat, you have enough work energy to get past that repulsion and get to the central atom and attack it and break bonds. However, in a lot of reactions, what will happen is, let's say we have a water solvent, and I'll represent that here with green. The water solvent will come in, and let's say we have a water molecule. This is negative, and our water molecule is polar, so it has a positive end. And so what the water molecule will do is it will pull off one of the 4 atoms that are attached to the central atom. So what you have from there is you're converting a tetrahedral into trigonal planar. Once you pull off that 4th atom, you now only have 3 things around the central atom, so you have trigonal planar. So it's all in one plane. So now you can attack it from the back side without any repulsion, or you can attack it from the front side without any repulsion. But that process, which is called solvolysis, that process takes time. So that would be one example of something that would have a slow reaction. So these things that are covalent tend to be tetrahedral, and they tend to have to change shape to a shape that's compatible, that allows particles to get in there and actually collide and break bonds. Okay, so collisions have to have enough energy to rearrange bonds to form products. I don't like that statement. That's from the book. Again, as an organic chemist, most of the times it's not a matter of collisions rearranging the bonds. It's a matter of something coming in there and helping it, something in the environment like a solvent. Molecules sometimes have to form activated complexes. Remember, we said activated complex is when all the reactants come together, right time, right place, correct angle on the functional group with enough energy to break bonds. The more complicated that process is, the slower it's going to be as a general rule. Okay, second factor, concentration. Well, of course, if we have more reactant particles in a given space, we're going to have more collisions per second. So higher concentrations tend to produce faster reactions, but I'll give you an example where it doesn't, and I'll use an analogy rather than a reaction. There are reactions that are called zero-order reactions, where the concentration has no effect on the speed. And it's sort of analogous to this. Suppose we had a classroom full of students. Doubling the amount of students, increasing the concentration, doesn't make it so that they can get out of the classroom faster, let's say that's our goal. What determines how fast the students get out of the class is the size of the doorway. So you would have to widen the doorway, not increase the number of students, and that would be analogous to reactions that are called zero-order reactions, which we'll talk about in another video. But usually, increasing the concentration increases the speed because you're increasing the number of particle collisions per second. Second, how does pressure affect a reaction? Well, pressure affects only one phase. What phase is it? The gas phase. So yeah, if you increase the pressure, it's analogous to increasing the concentration. But they're generally the same thing, except for pressure deals specifically with gas phase reactions. How does temperature affect reaction rate? Good question. Two ways. One, it speeds up the particles so you get more collisions per second. These are good things to put in your notes. Two, not only do you have more collisions per second, but the percentage of collisions that have enough energy to break the bonds also goes up. Now the question is, can you get to a point where the temperature is so high that 100% of your collisions, remember that Maxwell-Boltzmann distribution, not all particles at a given temperature are moving the same speed, right? If we were to draw the Maxwell-Boltzmann distribution, we look at particle speed, and we get, sorry, I drew that wrong. This is actually moles of particles versus velocity. You know, most of our particles are moving here near the average, but we do have some slow movers and some fast movers. So suppose that average represents the barrier where you have enough energy to break bonds. Well, by increasing the temperature, eventually you'll get to the point where all of these particles, or just about all of them, I could draw it better to show all of them, you get to the point where all of them have enough energy to break bonds. Now, practically though, that's really expensive, right? And not only are you breaking bonds, but you're not just breaking bonds at your functional groups where you can control the products, you're also breaking bonds everywhere. So there's really no sense in increasing the temperature up to a point where you get 100% effective collisions because you can't control what it is that you're creating. Fourth factor, surface area. Now, if you have a homogeneous reaction, those materials are considered what they call miscible. They're dissolved into each other, and there is no barrier for the reaction to occur. But in heterogeneous reactions, where let's say you have a gas that's reacting with a solid, if you have a solid and the solid is in a clump, here's my solid, then the gas can only hit the surface of the solid. It can't react with the materials that are in the core of the solid. But you can increase that surface area by grinding it up into a powder And by grinding it up into a powder, now you expose more of the solid per second, so you get more collisions per second. Reaction must take place on the surface of the solid or liquid. How does the amount of exposed surface area affect the rate of reaction? And we just said, again, if we increase the surface area, we get more collisions per second. But on another sense, it may be well to decrease the surface area so you can control the speed of the reaction. Tablets for medicine, for instance, are encapsulated in a cellulose material. That's where you get that capsule, that pill. And so this way, when you ingest it, it's reacting only with the surface of the tablet, and then the medicine is released slowly over time as you work your way towards the core of the tablet. If you grind the medicine up into a powder, then you're going to get the effects of it almost immediately, and that can actually be dangerous. And the last factor is the presence of a catalyst. Says that a catalyst lowers activation energy. In other words, a catalyst is going to provide a different way of running the reaction. And I'm going to get into catalysts in a little bit more detail in the next video. Now there are two, I'll get into detail in the next video. So the next video I'll talk about the difference between homogeneous and heterogeneous catalysis, and we'll look at inhibitors. So let's just take a look at this as a review. Oopsie poopsie. Okay, stole this picture. All right, first of all, reaction rates are based upon what we call collision theory, that there are really two factors here. I say everything has to come together, right time, right place, correct angle on the functional group with enough energy to break bonds. And I'm trying to make a point of that it's not always easy for a chemical reaction to occur. But there's really two main things. You have to have the correct angle for the collision, and you have to have enough energy during the collision to break the bonds, to break the Coulombic attraction between bonded particles. One of the things that we can do is we can increase the concentration of the reactants. In fact, this is one of the easiest things that we can do. By adding more reactant, we have more collisions among reactants, and therefore we have more collisions per second, so we have a faster reaction. Increasing the temperature. Again, not only does it increase the number of collisions per second, but it also increases the percentage of particles that can produce a successful collision. We said that an increase in pressure is analogous to an increase in concentration. It just involves gases. That was surface area. We can speed up a reaction by taking a solid and grinding it up into a powder, exposing more of the chemical per second. And then lastly, we can use a catalyst, which will provide an alternative pathway. In other words, lower the amount of energy needed for the activated complex to form by providing a different way for the reaction to occur. And again, I'm going to go into detail that in the next video. So that's the factors for chemical reactions, and thank you very much.